Pretty much everything we've been doing for the last 2 weeks or so has been leading up to one of my all-time favorite theorems. This is Steinitz's theorem. So today we're finally going to show that every planar three-connected graph can be realized as the edges of a convex polytope in 3D. Let's do it. So first of all, what the heck is a polytope? First, I guess we should define polyhedra. And a polyhedron is just an intersection of a finite set of half spaces. So a half space is the set of solutions to one linear inequality. So you could think of a half space as a set of all points x such that n transpose x. I use the transpose here as for dot product, right? So this is the dot product of some normal vector x. It's less than or equal to some constant. And you can think of that constant sort of as telling you roughly how far in the direction of the normal vector is the plane. If it was an equality, it would be the plane which bounds it. But it's a half space, so it's everything less than or equal to that. So it's everything on this side is the half space. All right. Now, if I have such a collection of half spaces and I take their intersection, so let me just do it in the plane. These definitions don't actually depend on the dimension so much, but let's say I take a bunch of half spaces. Let's take different varying sides. What I get is this region in here. So in the plane, a convex polygon is also a polyhedron. You can write it as the intersection of the half spaces that go through the edges. And polytopes are what we will call bounded polyhedra. And what I mean by that, of course, is, well, if you look at the half space, it goes off to infinity. Whereas if you look at this example, I can actually draw a circle around it. So if I can draw a circle around it or put it into a bounded sphere like this, then it's bounded. And so if I only had one half space, it would not be bounded. If I only had two half spaces, it would still not be bounded, unless it was empty, I suppose. In the plane, you need at least 3 half spaces to be bounded. In 3D, you're going to need 4. And so polytopes are bounded polyhedra. Now, if I have a polytope, then the polytope has what we'll call faces. And they are, I think, what you hope they are, although unless you hope that they're all the two-dimensional objects that we've been calling faces up until this point. Instead, there's going to be faces of dimension 0, which will be the vertices or corners you see in the polytope. Faces of dimension 1, which will be the edges where two faces meet. And then there's also going to be faces of dimension 2, which are these flat pieces. And so maybe to distinguish them from what we've been calling faces before, we'll call them facets. Right, so this is vertices, these are edges, and these are facets. And from this, you get a graph, because you can take just the vertices and edges of a polytope, and they form what we'll call a polytopal graph. Now, Steinitz's theorem is going to tell us how to characterize polytopal graphs completely just in terms of planarity and connectivity. Before we go to the hard part, let's do what I think is probably the easier part, is to see that polytopal graphs are planar. And I guess the most popular way to show this is by some crazy picture like this one. Up here, I have the polytope. So this thing right here is my polytope. And if I were to arrange it in space so that the top face is horizontal, so I make the top horizontal, and I take a point above that horizontal face, and I guess I put it pretty high up here. And the reason I put it high up was just so that the projection would stay on the page. But I'm going to take that point and I'm going to project through that point down to the plane. Okay, so for instance, that point, say it's up here. As it goes through, it enters that face, that top horizontal face, and it leaves again at this vertex. And so when it hits the bottom plane here, down here, this is R2 sitting down at the bottom. When it hits that, that's where I'm going to put that vertex. And it's not too hard to see that for two vertices, the entire edge between those two vertices will get mapped also to a line segment. So we're going to get a linear drawing whenever we do this kind of projection. And if you put the point really, really close to the top, what happens is you're also going to get an embedding. And the reason it's an embedding is that if two edges crossed, well, that would be a point where they cross. Let's pretend down here there was a crossing between two edges. If I look backwards by going back up to the point I was projecting from, then I would have had to hit two different edges. But that's actually not possible just because of the convexity of this polytope. So half spaces are convex, the intersections of convex sets are convex, so these polytopes are convex. And so when I hit an edge, I'm not going to hit another point until I hit that top face. So I can't hit two edges, and therefore the projection won't have two edges hitting the same point, and so I get a nice embedding just from this projection. There are variations of this idea to project higher dimensional polytopes down one dimension as well, but I'll leave that for another class. So the polytopal graphs, they're at least planar, and they're also three connected. And the way to see that they're three connected is to use an idea that we already saw when we talked about Tutte's algorithm. So if you remember in Tutte's algorithm, one of the key ways of constructing paths to connect vertices was to use monotone paths, so that in any given direction, you could always move from one vertex to another vertex that gets further in that direction until you reach the farthest point in that direction. Well, that idea is sort of most naturally embodied in polytopes. So polytopes also have this property, and if you've ever studied linear programming, the simplex algorithm literally tries to find a monotone path where the direction of monotonicity is the objective of the linear program. So we're going to do the same thing here, and it works like this. If there was a cut of size 2, then I can always find a line. I take the line through that cut, and for any other pair of vertices, so let's call this U and V, for any other two vertices, I can always find a plane that passes through this cut, actually that passes through this line here, and does not contain, that doesn't separate U and V. And so if I take monotone paths away from that plane, they'll both paths will reach the extreme point in this direction, and the concatenation of those two paths gives me a path from U to V that necessarily did not go through the cut set. So that would be a contradiction to the claim that this was really a cut set, because no matter what two vertices I choose, I will still have, for every other pair of vertices, I will still have a path between them. Okay, so this is somehow explains how the three-dimensionality gives you a three connectivity. So we've seen then that polytopal graphs are planar and three connected. The way more interesting, challenging case is the converse of that statement, which is to show that if your graph is planar and three connected, then it's actually that there is some polytope whose vertices and edges are exactly that graph. So if you want to think of this as an algorithmic problem, you might say, hey, given a planar three connected graph, maybe I can find the polytope. That would give me a constructive proof. And we almost have such a construction. We're like so close. Here's the thing you might try if you just follow the pure logic of the order of videos that I produced. You might say, well, I could run Tutte's algorithm. And Tutte's algorithm will give me a nice convex embedding in the plane. And then something about Tutte's algorithm should recall the Maxwell-Cremona correspondence, because it had this equilibrium stress condition, at least except for the outer face, which is going to be our trouble spot. But except for the outer face, you have an equilibrium stress. And so if we could really make an equilibrium stress, then the Maxwell-Cremona correspondence would tell us how to lift it up into 3D. And then we'd have to ask, how do we check or make sure or find out if that lifting actually gives us a convex polytope the way we want? Okay, so this is the rough algorithm, and now we got to show how to kind of tighten it up and make it work for real. All right, so one important geometric fact about the Maxwell-Cremona correspondence is that if you look at two faces after they get lifted, well, a valley fold like this, these terms, mountain folds, are the ones that go where they've kind of folded down, valley is folded up. I think these are the terms that are used in origami. Well, it turns out that a valley fold corresponds to a positive stress, and mountain fold is a negative stress. So when I put a spring constant on this edge and I find the equilibrium, if it is an equilibrium, then if there was a negative spring constant, it's going to form a mountain, and if it was positive, it's going to form a valley. And if you recall in Tutte's algorithm, all the spring constants were 1. So if we had a good lifting, if it was an equilibrium everywhere, then all of the folds will be valley folds, which is good because that means that it really will be convex. And I guess I need to wave my hands for this, because if everything is bending up, right, as you lift, then this object will be convex, at least the lower part. We still have to deal with the outer face, okay? But this idea that somehow if it's everywhere locally convex, everything is bending the right way locally, that globally it's also convex. That's what we're going to get to. So if I try to use my standard approach of solving a linear system in order to find the lifting, one thing you might remember is that I kind of only need to solve it on a spanning tree. And there is a spanning tree here that does not depend on, or doesn't intersect, doesn't use any of the edges of the outer face. Okay, so if I take this solution that I get this way, so that is, I solve the subset of the co-boundary system corresponding to this spanning tree, then I will get a lifting, but I may not satisfy all the equations. That is, I won't satisfy this condition that the outer face stays flat. Okay, so it's the one case where I didn't have equilibrium, and therefore it's the one case where the outer face might not be flat. But everything else works, so I can fold it up. I can lift this up so that all the folds are nice valley folds, except that it might just be kind of ragged on the top. That is, it might not all lie on a plane after I lift up these faces. It's very close to being a correct algorithm now for realizing the polytope associated with the graph. One case is easy. So there's one case where I think it really is not too hard to see that we would be fine, because if the outer face was a triangle, when we lift it up, it turns out we can never be wrong. Like, we can never lift up a triangle in a way that makes it not flat, because any 3 points in R3, there's a plane that passes through them. So in that one special case where the outer face is a triangle, everything works, and we just run the algorithm exactly as we did, ignoring the equilibrium stress on the outer face, and it turns out we'll still get a valid lifting, and it will be a nice convex lifting. So that's pretty good if we had a triangle, but what if there's no triangle? So what if G has no triangles at all? Then we're in a bit of a tough spot, because if we just run the algorithm as we have it, we'll get everything lifted up except for that outer face. It just won't be flat. So here's a crazy idea. Let's, instead of looking at the graph itself, maybe we'll look at the dual of the graph, because we are dealing with a planar 3-connected graph. So it turns out that if G has no triangles, then his dual graph does have a triangle. Why is that true? Let's check. There's 2 things we need to look at. First of all, if it has no triangles, then every face has at least 4 edges. So if I count 4 edges for every face, every edge gets counted there twice, once from each side. So this is the condition that all faces have at least 4 edges. And here, if, on the other hand, if there's no triangles in the dual, that means the dual faces all have at least 4 edges, or in other words, the degree of every vertex is at least 4. So this is all vertices have degree greater than or equal to 4. Okay, so these are the two conditions. Now we're just going to plug it into Euler's formula. Right? Because remember that Euler's formula is going to tell us for these connected graphs that 2 is equal to this number of vertices minus the number of edges plus the number of faces, which now we know is what? It is less than or equal to half the number of edges, right? Because v is less than or equal to half the number of edges minus the number of edges plus f, which is also less than or equal to half the number of edges. But if you add this up, this is 0. So it's saying that 2 is less than or equal to 0. Well, that's not possible. There's our nice contradiction. So it can't be the case that both G and its dual have no triangles. At least one of the two graphs will have a triangle. And we know then if you have a triangle, we can run our algorithm and get a polytope. Seems a bit weird, because if I wanted a polytope for G and I get a polytope for its dual, I'm not sure I should be necessarily happy with that. But here's the trick. So let's let P be the polytope for G star. If we assume that 0, like the origin, is inside the polytope, so we can move the polytope so that it contains the origin, then it's a polytope, so it's the intersection of some half spaces. Let's say that these are the half spaces, okay? So they're defined in terms of some normal vector, ni, and I scaled the normal vectors so that it's always the case that it's the set of all points x such that x times ni is less than or equal to 1. Well, there's this object, it's called the polar of P, and there's a general definition of how to take a polar of any set, but in this particular case, this polar will be equal to the convex closure of this set of all these normal vectors. Seems like an odd thing to do, right? So this take all these normal vectors, think of them as points, take their convex closure, it's a different polytope, and really amazing theorem is the following. This P polar is the polytope for G. So when I took my graph and I took the polytope for its dual, and I took the polar of that polytope, it turns out that that new polytope I get actually as a graph actually gets us back to G. Okay, so this last part, this kind of geometric structure, I'll point you to my favorite book on this subject, at least for this particular topic, is A Course in Convexity by Barvinock. And so I'm not going to go through all the combinatorics to show you sort of why the faces, the vertices and edges match up in this nice way. But suffice it to say that once you have this, then you do have a polytope, right? So now I have a third step in my algorithm. If I don't have a triangle, I take the dual, I embed the dual graph with the triangle as the outer face using Tutte's algorithm. Then I use the Maxwell-Cremona Correspondence to lift that to a polytope, and then I take its polar in order to get a nice realization of the polytope for G. Okay, so this is a kind of a direct, well, mostly direct constructive proof of Steinitz's theorem.